present some basic properties that quantum field theories have that we always have in the back of our mind when you think about quantum field theory. So the intuitive definition of quantum field theory is it describes a system which has degrees of freedom in any region of space, independent degrees of freedom for separate regions of space. So a way to think about this is that for every region of space, there is some algebra of observable that tells which kind of questions you can ask about this region. And if you have a subregion, well, the questions you can ask about the subregion will be part of the questions you can ask for the whole region. And if you have separate regions, the questions you can ask must be independent. This is the most crucial property, so locality. There is no, if you ask a question at this point of space-time, it can only influence what happens at some point which is in communication with that, not some space-like separated point. So if you take a limit where you think about very, very small regions, infinitesimal regions, you get to the notion of local operator. So the local operator is a sort of a question you can ask about a point or the immediate neighborhood of a point. So in a quantum field theory, typically you imagine that to each point there is an associated vector space of local operators. And the most basic questions you can ask are correlation functions, expectation values of a whole bunch of these local operators placed at various locations in space-time. This is not necessarily the most useful observable that you can think about. When I learned quantum field theory in high-energy physics, I don't think correlation functions were mentioned until very late. Because in particle physics, you want to think about scattering. The basic problem you have is if I throw in some particles, which particles come out? If you study some material, you might want to know what happens if you attach some electrodes to it and run some current to it, some transport properties. But all of these other bigger space of observables can be reconstructed given the correlation functions. So correlation functions are a useful sort of set of questions which capture a lot about the quantum field theory. And indeed, some of the axiomatizations of quantum field theory are just a set of properties that correlation functions should obey. Now, I should warn you that correlation functions of local operators are not everything. Topological quantum field theories often have no local operators at all. And still, they are non-trivial quantum field theories. So it's clear the correlation functions of local operators don't capture everything. But there is a general expectation that local operators capture the dynamics, capture the local dynamics of what's going on. And if there is anything else that is needed, it's something topological. So if you want, there is a general problem that you might ask, and is asking concrete examples. If I have a quantum field theory, what do I need to give you to present this quantum field theory, to describe it? And local operators are surely part of the story. And then there must be some other topological data. And what is the correct topological data to attach to a given quantum field theory is pretty much an open question, and quite an interesting question. For example, a situation where this thing could occur, right? Where you could see the difference between quantum field theories which have the same local operators and different topological data is that if you realize them in condensed matter systems, you try to deform one into the other. If the topological data is different, they will be phase transitions, even if the local dynamics look the same. Now, the simplest possible quantum field theory that we learn about is free quantum field theory. So there is some basic observables which are the fields themselves. These sort of classically, they are these functions of space-time, like the electric potential. And definitely a basic question you can ask is, what is the value of the field at this point? So these are local observables. Other observables might be derivatives of the fields, polynomials in these derivatives, up to equations of motion. And correlation functions in electric field theory are just Gaussian. They're computed by weak contractions, paying a bit of attention to normal ordering. Now, A more general class of theories that we feel confident exist and we study a lot are asymptotically free interacting quantum field theories. So these are theories that, morally speaking, are thought of as free field theories with some interactions turned on, some polynomial terms in the Lagrangian. But these interactions have the property that they become weaker and weaker at short distances, which means that roughly what's going on at very short distance is the same as what would go on in a quantum field theory. For example, the local operators are roughly the same as you would have in a free theory, which means that the questions you can ask from your theory are pretty clear. Finding the answers is very hard, but the questions, at least, are reasonably clear in terms of correlation functions of local operators. Now, they might not be terribly useful questions because as the interactions might become large at large distance, your local operators in a very small region of space-time might do something to your theory, which is very difficult to interpret at low energy. I don't know, in QCD, if you put a local operator at some point of space-time, it will produce a gigantic shower of particles scattering everywhere. On the other hand, building an operator that creates a proton would be very tricky. But still, at least conceptually, you know the questions. Now, let me go back to a free field theory for a moment, just to show that local operators built out of, even in a free field theory, local operators built out of your elementary fields are not everything that you can think about. There are more questions that you might want to ask. This is true especially if you have some kind of gauge symmetry. So the simplest example I can think of is that you have a scalar field in 2 dimensions, a massive scalar, and you want to gauge a reflection symmetry that sends phi to minus phi. It's usually called an orbifold in 2-dimensional quantum field theory. Now, this is a very simple operation. If you look at the local operators of your theory, because you're identifying phi and minus phi, you have to throw away some local operators. Phi itself is not a good observable because it's identified with minus phi. On the other hand, phi squared is definitely a good observable. So you take your local operators, you split them into even and odd, and you throw away the odd operators from the set of questions you can ask. Now, what's fun is that new questions emerge. New local operators are called disorder operators. A way to define this disorder operator in a free field theory is that you do your path integral on field configurations which are antiperiodic around some point in space-time. That's what it means to put a disorder operator at that point. You can also think of, now, you might find it strange that by doing something relatively topological like this, that doesn't actually change the dynamics of the theory. The set of operators would come in and out so easily. I should stress, this operation does not change, say, the scattering matrix of your theory. Well, this was a free theory, but in general, this sort of discrete identification would not change the scattering amplitude. It would just tell you that on some compact space, you want to put an even number of particles of odd charge, or something like that. Now, a way to think about what's going on is that in the original theory, you had your local operators, even and odd. And you could also consider situations where you put this sort of cut across which phi goes to minus phi. This operation looks pretty drastic, but because this is a symmetry, it's actually pretty mild, in the sense that you can move this cut around. It's topological. The answer of your calculation does not actually change. But the disorder operators are the sort of things you can put at the end of a cut. The cut itself can be moved around, but if the cut ends, something non-trivial happens. In the orbit-folded theory, what's going on is that you throw away the odd operators. Once you throw away the odd operators, you're unable to see this cut, because the property of this cut is that odd operators change sign across it. So the cut is gone, and these other operators can just sit there by themselves. On the other hand, the odd operators can still be found in the theory, but not in isolation. You need something called a Wilson line, which is, again, a topological line. And at the end of that Wilson line, you can put the odd operators. So the difference between these two theories is sort of topological. It's about which of these topological lines you include. And depending on the choice, you end up including some local operators as true local operators and some other ones as endpoints of lines. Now, let me give other examples of disorder operators. If you study gauge theories in 2+1 dimension, you will typically encounter monopole operators. Monopole operators are defined by removing a point from space-time and requiring that some units of flux thread the sphere around that point. Now, these disorder operators like this, the ones in the scalar field or these monopoles, are often important in applications. They can occur in many different ways. They can be order parameters for phase transition, for example. In some phases of 3D gauge theories, monopoles get eved. They can create solitons. If in the previous example, if you added some potential to the scalar field theory so that there are two minima of the potential at some values of phi, say 10 and minus 10, whatever, then you can have the theory typically gains new dynamical excitations, which are solitons, where the field goes from one minimum to the other of the potential along space. Disorder operators create these solitons, are the operators which create one soliton. Monopole operators can be thought of as operators that create a lump of flux. So sometimes in gauge theories in 3 dimensions, lumps of flux behave. There are solitons which carry some lumps of flux, and these are created by these monopole operators. And finally, these operators, these disorder operators, which are not simple functions to the elementary fields, can actually appear in the action. So it's perfectly possible to have some low energy effective action where you integrate away some degrees of freedom in the UV. And the effect of integrating away those degrees of freedom is to add some monopole to your action, or some disorder operator. This is quite terrible for computational purposes, because once you have a disorder operator in your action, you don't know what to do. But it definitely happens. It's very important for the physics of theories in 2+1 dimension, for example. Now, until now I discussed local operators. These are not the only sort of observables that you can consider in a quantum field theory. In the picture here, I was discussing some topological lines. Now, in general, it's possible to consider observables, or modifications of your theory, probes, which are maybe extended along a line or a surface or some other manifold of some codimension in your space-time. Typical examples are Wilson loops for gauge theory, which sort of measure the monodromy of the gauge connection along a path. Tooth loops in 4-dimensional gauge theories, which are defined the same way as monopoles, but because they're in 4 dimension, they extend along the line. You can have boundary conditions and interfaces between theories. You can just take a system and couple it to a lower dimensional system. All these sort of extended defects are fun, are interesting. They've been occurring all the time in my work. But I will just ignore them for the rest of the colloquium. There is just no time. I think there is no time in the sense that I don't have the time anywhere. So I'm completely lost in time. Now, let me go back to the orbital for a moment. I was doing it for a massive scalar field, but let's do it for some generic quantum field theory with Z2 symmetry. As I said, there are some even and local operators under the Z2 symmetry. It turns out that the disorder operators can also be distinguished into odd and even. Now, it's not completely canonical to say these are the even ones and these are the odd ones, but it's definitely true that you can separate them into 2 different classes, with the property that if you multiply one of them by O minus, by odd operators, you'll end up in the other class. So that means that there are essentially 2 different ways to gauge a Z2 symmetry, to take an orbit fold. You can keep even operators and even disorder operators, or you can keep even operators and odd disorder operators. So we end up essentially with three theories, the original theory and these two different orbitals. These operations are different. For example, those of you who know what the 2D Ising model is might also know that if you gauge the Z2 symmetry of the Ising model in one way, you get back the Ising model. This is called Kramer-Vanier duality. On the other hand, if you gauge it the other way, you might get the theory of free fermions, which is the reason Onnesager could solve the Ising model many years ago. So now we have three theories, and they all share the same set of operators, the ones in O+, these even operators. Is there anything else we can do? How do I know which operators can include in a theory, or which do I have to include? When do I stop? Of course, right, in a free or asymptotically free quantum field theory, roughly you understand what's going on, but the distinction between order and disorder operators is not God-given. It's perfectly possible to have a quantum field theory which has two different descriptions, and in one of them, the order operators are fields, and the other one, the one that are disorder operators, are now fields of a different theory. So why can't I, for example, just keep the even operators and forget about everything else? What goes wrong? Now, there are two things that can go wrong. Which one you want to look at depends a bit on personal preference. One possibility is to look at the quantum field theory on a space-time of non-trivial topology. Let's say Euclidean space-time, so I can put a theory on a torus. Compactifies Euclidean time and space. If you do that, when you do that in the original theory, you have some choices, because you could take your odd fields to be periodic or anti-periodic around the two directions on the torus. There are about 4 choices. If you're looking at correlation functions of even operators, though, you don't even see which periodicity you choose. Which means now you have 4 candidates possible correlation functions for your O+ operators on the torus. And you need to pick which ones define a theory. How do you decide which ones define a theory? Well, a useful exercise to do is to take your torus and start deforming it continuously. It's possible to deform a torus back to itself in a non-trivial way, in a non-contractible way. So that the torus goes back to itself, but the path you follow in a space of shapes is non-trivial. These sort of operations are called the mapping class group. Now, if you have a true theory and you compute a partition function on a torus, the answer is you just have an answer with the correlation function. It does not matter which path did you follow to get to the torus. Which means that among all of these solutions, you need to pick those which are fixed under the mapping class group. This is called modular invariance in two-dimensional conformal field theory. When people started solving rational conformal field theories, they discovered that in that particular setup, they had to first find an operator algebra and then impose modular invariance of the torus partition function. But it's a more general notion. It applies in greater generality. Okay. Now, of course, you could say, I don't care about space-times of non-trivial topology. I just want to do my physics on a plane, in Euclidean space, in Euclidean plane, or flat space-time. And that's fine. Now, depending on your theory, as you do scattering of even excitations, you might easily find that among that unitarity forces you to consider also excitations which are odd under Z2, if the Z2 symmetry is unbroken. If the Z2 symmetry is spontaneously broken at low energy, you might find that among the excitations there are these solitons. So now, it's a bit strange to work in a setup where you don't have operators which can create your particles. So the natural thing to do is to start from the opposite direction. Instead of keeping only the even operator, let's keep all operators. What goes wrong? Suppose I keep even and odd order and disorder operators? Well, the thing that obviously goes wrong in correlation functions is that they're not single-valued anymore. If I have an odd operator and a disorder operator, and I carry the odd operator around the disorder operator, my correlation function switches sign. So you lose a bit of locality. The answer does not just depend on what the situation is, but on how you got there, again. So you really get a collection of braiding phases. Right? There will be a space of possible correlation functions on the plane of all of these operators, and then non-trivial monodromies as you braid the positions around. You get some representation of the braid group. And again, a true quantum field theory will be a collection of operators and of correlation functions for which the braid group action is trivial. Now, if you've worked with topological systems, with gap phases of matter or this sort of subject, these two situations where you have a vector space attached to a manifold with a non-trivial action of the mapping class group, or a vector space, the space of correlation functions attached to the plane with points on the plane, and a non-trivial action of the braid group. These situations occur precisely when you study gap systems in 2+1 dimension, and you think about what happens to this system you compactify on a space on a non-trivial topology. Or when you look at the behavior of excitations in these systems, which might have an Ionian statistic, and so non-trivial braid group braiding properties. So, in particular, there is this theory called the toric code, which is the best studied toy model of topological systems in 2+1 dimension, which has precisely the property that the space of ground states of the toric code on a Riemann surface is just identical to the space of possible correlation functions of this 2D theory, generic 2D theory on that same surface. And also, it has 4 possible types of excitations which braid among themselves precisely in the same way as even and odd operators, order and disorder operators. So you can sort of solve the problems of this 2D theory, the multivaluedness of answers, by combining it with the toric code. So you can have a picture like this, where there is a 2D theory, which lives at the boundary of a 2+1 dimensional theory. And at the boundary, you allow yourself to put even operators, but all the other operators are only allowed if they lie at the end of a word line or some particle in 2+1 dimension. So you can take these 2 perspectives on this. One perspective is that you had this 2D theory that was somewhat sick. You glued it to a 3D theory, and it became okay. The opposite perspective is that another related perspective is that if you have some material, some system, you'll never be able to find a theory which has all these operators simultaneously. But if you have the toric code realized in some material, it might happen that at the boundary of that material, this theory might occur. So, and this is sort of a general phenomenon. Very often, it happens that you have quantum field theories which are somehow incomplete or anomalous or some mild sickness. The local operators work okay, but globally there is some trouble. And then you can build a topological field theory in 1 dimension higher, a topological system in 1 dimension higher, which captures these anomalies, these troubles. This is actually one of the ways topological field theories were discovered. The axioms of topological field theories in 2+1 dimension, the mathematical structure called modular tensor category, were discovered originally by Moore and Steinberg by studying 2-dimensional rational conformal field theories. In that setup, they had some. So in 2-dimensional conformal field theories, sort of you can separate holomorphic and anti-holomorphic dependence. Your operators naturally factorize in the product of some holomorphic operators and anti-holomorphic operators. But the holomorphic operators by themselves are not really okay. They're monodromies as they go on each other. And so in studying the failure of this holomorphic theory to work, they discovered the axioms of 2 plus 1 dimensional topological field theories. Conversely, topological phases of matter are very often identified or characterized by which quantum field theories live at their boundary. They're called the edge modes. What time is it? Sorry. Okay. So topological field theory. So I'm going to define in a moment what I mean with topological field theory. I used this term already several times. But so there are a very interesting subclass of quantum field theories, which is simpler, and it occurs in a variety of situations. As I said, they appear as anomaly theories for quantum field theories. Sometimes you can encounter them when you quantize actions for fields, actions which are topological. For example, at some point, people started studying Chern-Simons theory, which was an action for a gauge field. The action just did not contain the metric, so there was a good chance that the theory would be topological. Just topological quantum field theories occur when you study gap systems. Another way you can think about them is that they are just a low-energy effective description of a gap system, which could be itself a quantum field theory, or maybe something more complicated. That's why they occur so much in recent work in gap phases of matter in condensed matter systems. Not all gap phases of matter are described by topological field theories, but a lot of them are. They occur in mathematical physics also when you study supersymmetric quantum field theories. I'll get back to that soon. And then they play a growing role in pure mathematics. So there is really a big subject now in mathematics, which is just understanding, defining, studying topological field theories. Now, what do I mean with topological field theory? I think the most economical definition I know is that it's a quantum field theory where the local operators are locally constant. Now, it's not a terrible way to axiomatize, not a good way to axiomatize them because we don't know what a quantum field theory is. But it's a way to understand what their properties are. So there are quantum field theories where there are either no local operators at all, except the constant, or maybe there is a handful, but the derivative of an operator is just trivial. So because the derivatives are trivial, in particular there is no dynamics, time derivatives are trivial. It doesn't matter where you put at what time you do your observation. Only topology matters. There are no excitations. There is no S matrix. There is really no classical quantum field theory going on. But there are still non-trivial observables. They are quantum field theories, and they are non-trivial. I mentioned spaces of ground states when you make space, when you give space some topology. The statistics of heavy probes. Are they heavy probes anyonic? Are there heavy strings which braid in a non-trivial way around each other, around the particles? And sometimes they have non-trivial theories living at the edge. Meaning that if you realize one of these topological field theories in a material, in a system, and the system has a boundary, on that boundary there has to be something non-trivial going on. This is how they were sort of encountered first in condensed matter physics. Now, because there is no dynamics, we can hope to solve topological field theories. So we can hope to be able to fully characterize them and describe them and axiomatize them. This is a very active research topic in energy physics, mathematics, condensed matter physics, and quantum information. I find it interesting precisely because it receives insights continuously from all of these 4 different areas. Researchers in these areas look at topological field theories and topological systems in very different ways. They have different language, different intuition, different definitions of what a topological system are. But they are talking about the same thing. And we've been learning a lot from each other. So I started working on this subject about 2 years ago. I will not talk more about them, but I refer you to the talk I gave a month ago at the Simon Center for more details. Now, let me move to another class of theories which are definitely, which are potentially far from being a theory of quantum fields. So, as I said, in these asymptotically free theories, the interactions get turned off at short distance. So the theory becomes essentially free at short distance. There are quantum field theories which are never free. There are quantum field theories which, no matter at which energy scale, look at them, they are not free. In particular, the most glaring example are conformal field theories. Conformal field theories are quantum field theories which are just in scale invariant. They don't care about scale. So if a conformal field theory is just completely indifferent to the overall scale of the metric. This is called Wall invariance. So, which means a conformal field theory might be close to a free field theory or might be far, but whatever it is like that, no matter which questions you ask. It can be weakly coupled, it can be strongly coupled. Now, the good news is that we understand pretty well how conformal field theories work. So, because of this Wall invariance, because of the scale symmetry, which is a big extra symmetry, you can deduce some very striking facts. The most striking fact is that the whole, at least the whole local set of local properties of the conformal field theory are captured just by two pieces of data. One is the list of all operators and their scaling dimensions. There will be some infinite list of operators of increasingly large dimension. And the bigger the dimension of operator, the less important it is, in a sense, to understand what's going on in the quantum field theory. And then there will be a list of numbers called three-point function coefficients, which are the coefficients that appear in the OPE expansion. The OPE expansion is this fundamental property of conformal field theories, which tells you that if you have two local operators nearby in space-time, you can replace them by a sum over an infinite collection of local operators placed at one of the points. So if you have 2 points, you can replace them by 1 point at the price of having an infinite sum. This is not a formal thing. Maybe when you do perturbation theory, you learn that a lot of the sums you encounter in quantum field theories are divergent asymptotics. No, this is a convergent expansion, which means that in principle, if you have an endpoint function on a sphere or on a plane, you can compute it recursively by taking pairs of operators and replacing it by one operator and summing over. So endpoint functions are written as sums of n-1 point functions, which are written as sums of n-2 point functions, and all these sums are convergent. Furthermore, there is a strong constraint from associativity. You might contract your punctures together in a different order, and you should be getting the same answer. For example, if you have a 4-point function, you might first do OPE of operator 1 and 2, and then do OPE with operator 3, and then with operator 4. Or you could do 1 and 4, and then 3 and then 2. These two operations must give you the same answer. This gives you something called the crossing equations, crossing symmetry constraints. So these are equations that must be satisfied by the CFT data. This big collection of scaling dimensions, spins, and 3-point function coefficients, this big collection of numbers must be a solution of these crossing equations. Now, this is an infinite set of equations, an infinite set of variables. It's pretty daunting. It has been for a long time, a dream of using them to solve quantum field theories, to find quantum field theories. But for a long time, it could not be done except in very low dimension. So for a while, the only place where conformal bootstrap worked was in two-dimensional rational conformal field theories, which are a small set of two-dimensional quantum field theories, conformal field theories. Now, recently, though, starting from some research in Technicolor, actually, in particle physics, taking color models in particle physics. People realize that just by doing brute force numerics, they can actually do a lot of progress. So there have been, people have been able to essentially, for example, solve the 3D Ising model, which is a non-trivial conformal field theory in 3 dimensions. In principle, just by solving this equation, essentially the basic idea that they've been using is that you can combine the crossing equations with unitarity to get a lot of inequalities, big families of inequalities on the data of your theory. And when you just plot together all these inequalities, if you set it up properly, you're going to carve out very tiny spots in the space of possible parameters, which becomes smaller and smaller the more operators you include in your analysis. So I think at least potentially there is a hope that using the conformal bootstrap, people will be able to just find all conformal field theories with some properties, solve specific conformal field theories, compute in a fully computational way, given enough computational power, of course. Now, of course, this work is mostly numerical, although there has been some very interesting semi-analytic work. It raises some interesting conceptual questions, though. Suppose that somebody comes triumphant with a list of local operators and consistent OPEs and a table of 3-point functions. Is that it? Is this a conformal field theory? Presumably not. You still have to deal with things like modular invariance. My expectation, and not only mine, is that you will have to add to this local information some extra topological information. The hope is that there will be some algorithm that takes the CFD data, processes it, and spits out some topological field theory in one more dimension, which tells you what are the obstructions to having a full quantum field theory. And then within the topological field theory, you'll have to answer some question which tells you what to do. I mean, this was definitely the case in the case of rational conformal field theories, as I was mentioning. So there you had the topological field theory, which sort of was describing the obstruction to complete factorization between holomorphic and anti-holomorphic parts of an operator. And then you had to find something like a topological interface in this topological field theory, which would teach you how to glue them, holomorphic and anti-holomorphic parts. Well, the CFT does, but if you try to factorize it into holomorphic and anti-holomorphic parts, the holomorphic and anti-holomorphic parts individually do not make global sense. Well, a correlation function of, well, because the technology of conformal symmetry allowed them to solve for correlation functions all the holomorphic parts. And they found a vector space of solutions. And then there was a solution of the vector space of solution of the anti-holomorphic correlation functions. Then they had to find a bilinear in these vector spaces. They would produce a number, the correlation function of the full theory. And this pairing had to be such that if you transported holomorphic operator around and anti-holomorphic at the same time, the answer would not change. Don't have a theory. You have an algebra of local operators. That's right. Presumably. Now, it's possible that the topological data is trivial. I can very well believe that if you take the 3D Ising model and you list all the operators and ask, is that it? You'll stop. On the other hand, if you solve the Ising model but you forgot the odd operators, somebody gave you just the list of even operators, then there are actually two CFTs which have the same list of even operators. There is the 3D Ising model, and there is 3D Z2 gauge theory. They are related by this sort of orbit folding operation. And maybe, yeah, I think that's it in that case. So if you apply this machinery, presumably you'll find a very simple topological field theory, Zitschuk theory in 4 dimensions. And then you'll ask questions, you'll ask what are the topological boundary conditions for that? And this will teach you what are the full conformal field theories. It's also possible conceptually, although, and it would be very exciting if it happened, that somebody gives you a list of local operators and 3-point functions, and you find that there is no way to make it into a true theory. That means that this system has to live at the boundary of a topological system. If you find the topological system and you realize it in nature, you might find your conformal field theory living at the boundary. In 2 dimensions, this happens to chiral theories typically. So if you try to make a theory which has only left movers, only holomorphic operators, that cannot really happen in a real material, but it can happen at the boundary of a material. So that's how people got to studying the quantum Hall effect and noticing that there were chiral edge modes. They got it to relate it to topological field theory, to Chern-Simons theory. Okay, I assume 45 minutes passed? Okay. So now let me move to one final topic, which is supersymmetric quantum field theories. Now, this is a vast topic. There is no way I can make almost any justice to it. But still, let me try to say something. So what is a supersymmetry? A supersymmetry is a symmetry which relates bosons and fermions in a quantum field theory. If you're in a relativistic quantum field theory, the spin statistics theorem pretty much forces the supersymmetries to be spinors. And it also pretty much forces them to have a specific symmetry algebra. So two supersymmetries will anti-commute to translations. So supersymmetry is a bit different from standard bosonic symmetries like the Z2 symmetry Daisy model, in that it has to be mixed with translations. It had to be mixed with space-time symmetries. In a quantum field theory, you can have up to 16 supersymmetries. If the theory is conformal, you get for free another set of superconformal symmetries. So the maximum becomes 32. And the supersymmetry, the algebra becomes more complicated with conformal transformations on the right-hand side. Now, it's hard to say in general what are the properties of supersymmetric theories because they depend very sensitively on the number of supercharges and on the dimension of space-time. Actually, more on the number of supercharges than the dimension. But in general, what happens in supersymmetric theories is that supersymmetry can restrict severely how certain spatial observables depend on certain parameters. So supersymmetry, for example, might guarantee that some observable is not corrected by some couplings. Or it might guarantee that some couplings are only renormalized at one loop. Or so on and so forth. You get all sorts of non-renormalization theorems that tells you these cannot depend on that. These cannot change when you change that. So because of that, it's often the case that you can compute exactly these protected observables. Because you know they don't depend on certain deformations, they don't depend on certain modifications, you can often modify the theory until it becomes computable, and then compute those protected quantities. Now, these are only a very small set of observables, but sometimes are enough to understand the physics. I should stress that a lot of supersymmetric theories have a dynamics which is as rich as the one on non-supersymmetric theories. Supersymmetric Yang-Mills theory confines just in the same way as Yang-Mills theory does, with minimal amount of supersymmetry. But still, you get a little bit of extra information, which can be a very powerful hint. If you have a little bit of supersymmetry, you'll get a little bit of information. It can still be a powerful hint of what's going on. If you have a lot of supersymmetry, you'll be able to compute a lot. The dynamics might or not be still interesting. So from this point of view, supersymmetric theories are often very interesting toy models. that allow you to reproduce some interesting physics in a system where you have more computational skill. Now, there are also some aspects of supersymmetric theories which are very different from non-supersymmetric theories. For example, it's rare to find families of non-supersymmetric theories. The only example I know really is the two-dimensional theory of a scalar value in the circle, where you can change the radius of the circle. But families of theories of supersymmetric theories are very common. You can have moduli spaces of vacua, meaning that the same theory might have multiple vacua, a continuous choice of vacua. Again, this is very rare in non-supersymmetric theories, because in a non-supersymmetric theory, you always end up creating some potential that lifts this direction. In a supersymmetric theory, sometimes you can prevent the potential from happening. Also, you can have parameter spaces of exactly marginal deformations. Again, in a normal quantum field theory, typically your interactions have a beta function. They run somewhere. But in supersymmetric theories, you might sometimes prevent the beta functions from appearing. So you get quantum field theories which are on the nose conformal and have a tunable coupling. In particular, that means you can have situations where you can have some theory you understand well with a coupling that is small, and then you can tune it continuously and go somewhere. You can ask, where am I going? Right? Am I going somewhere else which I also know or not? And this way you get two sort of things. You might get dualities, or you may get exotic theories. So sometimes you follow some continuous path, you end up somewhere else, which happens to be a theory you already knew, but in disguise. So the operators, the fields, they organize themselves in a very non-trivial way along the path, and you get with something that looks completely different. Or sometimes you just land to somewhere new. So some exotic theories with no Lagrangian description. A general theme in studying supersymmetric theories and applying them to mathematics, for example, is that the protected data of a supersymmetric theory can be often organized in some coherent and intricate mathematical object. So if you know things about these quantum field theories, if you know non-trivial quantum field theory facts, I don't know, you might know things like this theory, I know this theory will confine, or I know this theory will undergo some Higgs mechanism and land somewhere else, or I know these two theories are dual. Then those physics statements can be converted into statements about these mathematical structures. Sometimes they are just obviously true. Sometimes they are very non-trivial statements, completely unexpected truths. So historically, there have been both situations where dualities or properties of quantum field theories implied completely unexpected new mathematical phenomena, or situations where mathematical phenomena which were already known turned out to exist because there was a quantum field theory behind, quantum field theory duality behind. So typically, some examples are the discovery of homological mirror symmetry from the study of 2D supersymmetric theories, the explanation of symplectic duality, geometric Langlands, and some knot homology in terms of 3- and 4-dimensional quantum field theories. There are also connections between these other topics, cluster algebra, Hitchin systems, and 4-dimensional theories with A supercharges. And I've spent years on this stuff. It's fun. It's very interesting. It's a bit of an acquired taste. You might wonder how much of it is physics, how much is it math, how much is it nothing, because you're not proving things, and you're studying theories which are not probably going to see outside. But you learn things. And then you try to apply those things to other situations. I've definitely learned a lot about how a quantum field theory might look like, which then I sometimes could apply to situations which had no supersymmetry or were topological or so on. Now, another thing I should say is that there is a close relationship between supersymmetric quantum field theory and string theory. So we have learned a lot about quantum field theory from string theory. Phenomena like holography, dualities, existence of exotic CFTs, all came first from string theory. And then they were purified in quantum field theory and then started spreading. An example which has been very relevant for me is the existence of some very peculiar six-dimensional conformal field theories predicted by string theory. Why is it? The reason this is peculiar is because there are no asymptotically free theories in 6 dimensions. So nobody knows how to build 6-dimensional theories which are not free, but they exist. And string theory gives you a whole collection of properties they have. And supersymmetry allows you to use these properties and transport them to a lot of other places. Now, you might say, okay, I don't care about 6 dimensions. We don't live in 6 dimensions. But if you take the 6D theory and you compactify a Riemann surface, you get a 4D theory at the end of energy flow. Supersymmetry might allow you to follow more or less what's happening along the energy flow. And so just by defining a handful of 6D theories from string theory, you might end up with whole gigantic families of 4D theories, which are labeled by the Riemann surface you use in the compactification. So for example, this way you could get these very large families of 4D theories with n equal 2 supersymmetry. It includes almost all Lagrangian theories we know, really almost all, up to 10 or a handful of them. But most of the theories in this family are not Lagrangian theories at all. The starting point, the 6D theory did not have Lagrangian, and this property is inherited. So this is a controllable setup where it's clearly evident that the theories we know are a small subset of the theories that exist, the quantum field theories that exist, and not a terribly representative subset either. So well, I first should spell out why am I sure that M theory exists. Okay. And I believe that M theory exists because there is a very coherent set of dualities that relates it to various string theories. And in principle, it has a definition based on holography. Then I also believe that M theory has specific objects inside, which are the sort of 6-dimensional membranes. And if I believe that, then I can ask, at low energy, what lives on a membrane? And this is the 6-dimensional theory. The 6-dimensional theory has the property that it gives a UV completion to 5-dimensional gauge theory. So 5-dimensional gauge theory is not normalizable. It has a coupling which is dimensionful in the wrong side. So in the UV, it becomes very strongly coupled. But there is so the conjecture or the expectation is that supersymmetric Yamil's theory is completed in the UV by this 6-dimensional theory compactified on a circle. So by collecting pieces of information like this, you can start deducing properties of these 4D theories. You can say, what is this? The algebra of protected operators, for example. And study their properties. And in particular, supersymmetry allows you to demonstrate that by compactifying the 6D theory on different Riemann surfaces, you get different theories. If you gave me a 6-dimensional theory, which is not supersymmetric, you told me, put it on a Riemann surface, well, something will come out, but nothing might come out. The theory might be just gapped on a Riemann surface, or the answer might be independent of the surface I compactify it on. But here, because of supersymmetry, you can protect enough information to know that what's going on in the infrared is non-trivial and different. With less supersymmetry, you can try to do similar things. It kind of work, a bit of work in progress. But again, it seems that you can build a big family of 4-dimensional theories with an equal 1 supersymmetry. And again, with pretty exotic properties that you wouldn't expect to see with our usual intuition, like E8 symmetry, as I was mentioning. Something else I can very quickly mention is that often these collections of protected quantities can be organized in a topological field theory. There's this trick developed by Witten, is a topological twist, where you identify a supercharge which squares to 0, and then you sort of take the cohomology of that supercharge, meaning you only look at correlation functions involving of operators which are annihilated by Q, and then you observe that operators that are in the image of Q drop out of the calculation. And so you get a sort of simplified theory which still captures all the protected quantities of the original theory. And this is one of the main tools used in the mathematical analysis of these theories. And also one of the setups which motivated mathematicians to learn how to define topological field theories and develop technology which can then be applied to more physical topological theories. Okay, so I think I'm pretty much done. So the main message I want you to bring away is that although quantum field theory has been defined many years ago, it's a subject which is still evolving. It receives insights from many different areas, in many different communities of scientists. These communities use quantum field theories in very different ways. They ask different questions. They define them in different ways. But whenever they discover something new in quantum field theory, this knowledge then can spread quickly to the other areas. Now, historically, this is what happened to renormalizations. Now it's happening with a lot of other things, like dualities, discrete anomalies for discrete symmetries, SPD phases, topological phases. There's been a lot of communication over the last few years. Language barriers can be still daunting. It can be very hard for me to read a condensed matter theory paper on quantum field theory, even if they're doing things I know, but just the language is just very different. The names are different. But with some effort, the language barrier can be overcome, and it's very useful. So if you're interested in working in quantum field theory, a basic advice is that you should learn to communicate across disciplines. You should be able to read papers from high-energy physicists and from condensed matter physicists and talk with them, and from quantum information theorists and mathematicians. Mathematicians are really grabbing quantum field theory and running away with it. For now, most of the work is in topological field theories or perturbative field theories. And already they're learning things which we don't quite know about, or learning to think in different ways about things we know. I hope and expect that they will keep going and surpass us in several directions in understanding quantum field theory. So you should just be open to learn in different ways. Personally, I'm not very knowledgeable about non-relativistic quantum field theories. Things like the conformal bootstrap do use relativistic symmetry in a very intrinsic way. So I don't have anything particularly significant to say. Well, it's not a quantum field theory. So gravity is not a quantum field theory. So it doesn't fit between quantum field theories. I think. Right, clearly I don't know how to think about quantum gravity. Well, I don't. First of all, a quantum field theory for me is almost by definition something that can be coupled to a background metric. So that, that kind of this. But I assume you want a deeper answer than that. Right. There is just no notion of region of space. So I cannot say, okay, I have observables attached to this region of space. Yes. Well, it depends on what you mean with the word exist. So if you have a CFT, right, and you deform it, like take the Ising model and turn on a mass, then definitely a low energy, your theory becomes free. There is a bunch of massive particles that go around and don't do much. And in the UV, there is the Ising model, so it's strongly interacting. What's not clear to me is that you can find a path integral setup where that thing can be described in a coherent way. So there is this hope or dream of so some people do hope that somehow you can constrain the RG flow of all operators as you go to UV and find some UV fixed point for your Lagrangian written terms of quantum fields. But I don't know of any situation where this has been made to work. So, right, so if the UV is strongly coupled, typically the UV cannot be described by path integral. As a quantum theory of fields. But it's definitely true that there are asymptotically conformal theories. That's what I'm trying to say. So there you can have a lot of situations where in the UV, the theory is not free, but it's conformal. I give an example of deforming a conformal field theory. Another example, we take a conformal field theory, which has a global symmetry, engage the symmetry. You have a gauge coupling now, it will run. If you're lucky, the beta function will be negative. So in the UV, you'll get back your CFT in a free gauge field. And in there, you'll have something else which is out of your control. I don't know if this answers your question. What does it mean, R? Unfortunately, you cannot do it in a translation invariant way. You can do R to 1 over R in a conformal field theory. In a conformal field theory, UV and R are identical. So you can indeed do a transformation X goes to 1 over X, and it leaves the conformal field theory unchanged. But it's because the conformal field theory has extra symmetries, which when you do that operation become translation symmetries. So typically we want translation invariant quantum field theories. Now, it's true that you could try to define something by taking quantum field theory which is translation invariant and saying, by fiat I take X to 1 over X in all my correlation functions, and I call this a correlation function of something else. But that something else will not have translation invariance anymore, unless the theory was conformal. Sorry?
If you think that screening mechanisms that can be obtained by deforming a theory, by adding extra derivatives, or by hand adding more degrees of freedom on it, a way in which you can achieve this asymptotical freedom in the theory?
I don't think so, but there is. I know some people hope that it could be possible to write some non-polynomial action, which has infinitely many terms and which magically conspire to be okay in the UV. But I personally have not seen it happen.
That would be very far away from being called conformal field theory, because normally those type of mechanisms that essentially wash away and are the answer for this consideration do depend on certain scales that just can pop up in the problem.
Okay, I'm not sure. So I'm not getting the question. What? Okay. Yes. Mm-hmm.
But I wonder what you would answer if you were forced to answer. So, you don't think that a Lagrangian you don't think a path integral is necessary?
No, I mean, as I said, I don't know the precise formalization, but I expect that the quantum field theory will be this assignment of this collection, these collections of local operators and rules on how to multiply them, how to bring them together, and extra topological information which is needed to select specific solutions of these word identities on a given manifold.
So when you say local operator, are you thinking that there must be a Hilbert space and so on? Or are you thinking algebraically that there's an algebra of operators?
Well, maybe if you think about algebraically, you should say, right, there's an algebra of local operators and then some extra topological data that teaches you how to build Hilbert spaces over which this algebra acts.
So you think of a representation in the end an important part of the theory?
Yes.
Okay, so before we think that we may run more time, I'll just remind you that it's Max and Keith Cody who has more questions there. And well done on attracting the crowd that didn't fit into the ballroom. And well done to you guys for showing up.
Okay. Well done for getting the room.
Yeah.